Hey everyone, I'm Jason Grant. I'm here with Maggie Zhang, and we're here to present a paper written by Daniel Firestone, an employee at Microsoft, for VFP, also known as the Virtual Filtering Platform, which is essentially a virtual switch platform for host software-defined networking in the public cloud. All right. Public cloud workloads provided by vendors such as Microsoft, Amazon, Google, and all the ones that we've learned about in class from so far. They have all grown exponentially in scale since the advent of cloud computing. It's not uncommon for vendors to often report server counts in the millions. These data centers have to provide its clients with scale, high density of virtual machines, high performance of virtual machines, and all this has to come in conjunction with providing rich network semantics, such as private virtual networks, customer supplied address spaces, scalable L4 load balancers, security groups, access control lists, virtual routing tables, bandwidth metering, quality of service, just to name a few. All of these policies are fairly complex, often too complex to be handled at scale in routers and hardware. So in order to implement policies that are complex like this, we have to implement them with virtual switches. These switches connect to virtual machines which reside in the network. This idea of implementing a complex policy for all of the aforementioned networking semantics that I gave earlier would allow the physical network, which consists of the core routers and any other hardware that's present in the network, to be more simple, more scalable, and faster. This idea is more formally known as software-defined networking, or SDN. SDN provides a centralized control council that is separate from the data plane operating on the host. This helps make the network more flexible and allows it to support the virtualized server and store infrastructure that a modern day data center needs to provide. Host-based software-defined network technology has been used to implement the virtual networking features that are currently used on Microsoft Azure, which makes sense given who is writing this article. However, much of the focus around SDN lately has been on network controllers and services being scalable and flexible, but not as much attention has been paid to the programmable virtual switch. The virtual switch is needed for a highly programmable data plane with high performance and low overhead. Microsoft originally had a virtual switch that was made up of networking filter drivers that were attached to Windows Hyper-V hypervisor, but this ended up not being very scalable. Alright, so the goals for VFP, you can see all of them in front of you. The first one being that they wanted to provide a programming model allowing for multiple simultaneous independent network controllers to program network applications and to minimize cross-controller dependencies. Other vSwitch models that were already on the market usually assume a single distributed network controller has complete control over programming a switch. As you can imagine, this probably wouldn't scale very well in a cloud environment where designers would often need to add logic to already existing controllers. This would eventually increase their complexity. Remember, some of these controllers are likely communicating with other controllers due to the go-tos in the match action table model. Instead, Microsoft needed a design that allows designers to build new controllers for newly added logic. These controllers should be able to create and program their own flow tables and to establish boundaries between these controllers in order to reduce complex dependencies. Goal number 2 for VFP was to provide a match action table programming model capable of using connections as a base primitive rather than just packets. The match action table programming model often only provided policies for packet classification, which were assumed to be stateless usually due to limited hardware resource availability. Remember, Microsoft wanted a connection classification instead, and stateful policies for its packets. Goal number 3 was to provide a programming model that allows controllers to define their own policy and actions rather than implementing fixed set of network policies for predefined scenarios. Other vSwitches, like Open vSwitch, which again I'll talk about later, had to provide added virtualization functionality outside of its MAT model. Microsoft wanted all functionality, including virtualization policies, onto the match action table model in order to push as much logic as possible into the controllers. For example, instead of having a schema that defines what a VNet or virtual network is, the VNet could be implemented using some programmable endcap and decap rules, matching appropriate conditions, etc., while leaving the actual definition of the virtual net in the controller. This would help greatly reduce the need to continuously extend the data plane every time the definition of a virtual net changes. The next set of goals for Microsoft's new vSwitch came about during their transition from VFP version 1 to VFP version 2. Goal number 4 was to provide a serviceability model allowing for frequent deployments and updates without requiring reboots or interrupting virtual machine connectivity for stateful flows and strong service monitoring. This was to handle increasing demand from other Microsoft engineers for more frequent updates with minimal downtime and strong service monitoring, all to help implement stateful flows. Goal number 5 was to provide a very high packet rates, even with a large number of tables and rules via extensive caching. As VFP grew more and more popular, flow tables with a ton of rules were created, which ultimately impacted performance since packets had to traverse these tables to find their destination. The solution was to compile flow actions across tables and use extensive flow caching so that packets didn't need to traverse entire tables to find their path through the network. Their final goal was to implement an efficient mechanism to offload flow policy to programmable network interface controllers without assuming complex rule processing. As more network interface controllers became part of the cloud network, a prohibitively more expensive hardware resources would be needed to offload these flow policies. Microsoft instead wanted a model that would sync with the pre-compiled exact match flows, which would allow hardware to focus on the support of a table of cache flow DRAM. At the time and during the development of VFP, there were other programmable virtual switches that were already in various stages of development. Linux and Windows already provided a bridging between interfaces that could act as a pseudo virtual switch. However, these bridges couldn't directly apply software-defined networking type policies. Google has their own plan for host SDN policies, but at the time of this paper's release, they decided to keep those details a secret. The main other vSwitch competitor was, or probably still is, Open vSwitch, also colloquially known as OVS. OVS is implemented using OpenFlow, and this combo allowed designers to create controllers that could manage virtual switches and physical switches via the same protocols. Although this is a very cool and awesome feature, it wasn't a necessary requirement for Microsoft's own vSwitch. One of the reasons why Open vSwitch wasn't used, and instead Microsoft decided to create their own, was because OVS doesn't natively support independent multi-controller models. This would obviously violate the very first goal of Microsoft's own vSwitch. Second, OVS doesn't natively support stateful actions in its match action table model. This would obviously violate the second goal of Microsoft's vSwitch, which did need to have stateful actions as a base. Third was OVS's VTEP schema, does the virtual tunneling endpoint schema. It didn't allow controllers to specify their own endcap and decap actions. This would obviously violate Microsoft's goal number 3 for their own virtual vSwitch. Next was that OVS does not support its own VL2 style directory system, which is required for customer address to physical address mappings. This would unfortunately cause packets to have to go all the way back to the central controller in order to find their desired mappings for their destination. This obviously would not scale very well for a large amount of packets that would need to track back towards the central controller. And last, the current OVS does not have a generic offload action language to support policy combos such as an ANATA NAT plus a VL2 style endcap system. This would violate the 6th goal that Microsoft had for their virtual switch, which was to provide offload full policies without requiring hardware to support complex multi-table lookups required in the original policy. Because of this, Microsoft ultimately decided that, hey, we need our own vSwitch in order to accomplish our goals. That vSwitch would eventually come to be known as VFP, a cloud-scale virtual switch that acts as a filtering engine for each virtual network interface controller of a virtual machine. This setup would allow controllers to be able to program their own software-defined network policies independent of those created by other controllers. VFP has already been deployed on over a million different hosts, running infrastructure as a service and platform as a service workloads. As you can see over there to the right, I included a colorful design of VFP, which I will discuss more in a little bit. One of the key design features of VFP is that it sits on top of Microsoft's Hyper-V switch. VFP assumes that the switch will have many ports that are connected to other virtual network interface controllers. VFP will then take traffic and filter it, take traffic coming from the virtual network interface controllers, filter it, and then send it to the Hyper-V switch, as well as vice versa in the other direction. Some other key features include that VFP implements its match action table with layering in order to support the multi-controller model, which is one of our key goals. It also processes packets through a slow path, fast path dichotomy through unified flow tables. It also provides a classifier in the match action table layers. The bridge that you can see over there in the diagram to the right also has its own switching model. VFP has their policies attached to a specific port based on an inbound and outbound model, where ingress traffic to the switch is considered to be outbound traffic from the virtual machine, and egress traffic from the switch is considered to be inbound traffic to the virtual machine. VFP also provides a switch abstraction interface that enables logic for management of ports, virtual network interface controllers, and a whole host of other objects. This interface also provides support for both Hyper-V extensibility as well as filtering for native hosts. The two can be seen respectively in the diagram on the right. The programming model used for VFP is based on a hierarchy of VFP objects. As you can see, some of them are listed, or they all are listed here. Controllers can create each of these objects as they see fit in order to implement their own software-defined networking policies. These objects include ports, which are the basic unit that VFP policy filters on, layers, which are stateful flow tables that hold match action table policies, groups, which are used to control related rules within a layer, and the rules themselves, which are the match action table entries. All right, VFP policies are implemented on a per port basis. This clean separation of ports allows controllers to independently manage policy on different virtual machines and instantiate and manage flow tables only on ports where they are needed. For example, a virtual machine in a virtual network could have tables with encap and decap rules for traffic into tunnels, which some other virtual machine that isn't currently in that virtual network doesn't really need to know about. Other objects, the other objects for VFP are all arranged in fixed hierarchies with priority values. These priority values help determine the order in which they will be processed in by rule matching. VFP divides a specific port's policies into layers. Layers function as a sort of a higher level layer of the match action table. Each layer can be created and managed by a different controller. One controller could even specify many different layers. When packets arrive in a network, they move through each layer one by one, only proceeding to a new layer based on the state of the match action performed in the previous layer. The order of the layers they traverse in the inbound direction is directly reversed in the outbound direction. Take, for example, the NAT design that you can see over to the right. In the inbound direction, the layer NAT's connections destined to the VIP to a direct IP. On the outbound direction, it NAT's packets back from the DIP to the VIP. This layer thus implements an address space boundary, where any packets above it are in DIP space, and any packets below it are in VIP space. Other controllers could choose to create layers above or below this NAT layer, and can plumb rules to match VIPs or DIPs respectively, all without coordination or involvement of the NIT controller. This inbound and outbound reversed action is helpful in implementing a stateful policy for our flow state. Any packets that say going on an inbound direction will be assumed to have a tuple, a TCP or UDP 5 tuple, going in the opposite direction on each of the layers. This encoding will be stored in a hash table for all the connections in either direction, essentially creating a paired inbound and outbound flow. So for example, whenever a rule is matched, say going inbound, an opposite outbound rule is also created in a flow table with the flow in the direction of the rule having the action of the rule, and the opposite direction, say outbound in this case, takes the opposite action in order to maintain layering. A key attribute is that VFP will only search for a single rule in each layer, because only one rule is allowed to match a packet in any given layer. Rules themselves are the entities that perform actions on matching packets for the match action table model. These rules help solve goal number 3 for Microsoft themselves, which will allow the controller to customize their own policy while minimizing fixed policy in the data plane. Rules have conditions, which if a condition is matched with a packet, it will then check to see what rule or what action needs to be implemented in order to satisfy that rule. For example, some example conditions could be a type, such as a source IP address, a list of matching values where each value can be a singleton, a range, or prefix. And then there's some actions. For example, you can allow or block a packet from proceeding further in the network, network address translation, and cap decap. More examples of which can be seen in the table shown to the right. All the rules on a layer are usually organized into groups for management purposes. Groups are considered the atomic unit of policy in VFP. Controllers and clients are allowed to update groups based on how they see fit. So a VFP will iterate through a group and will find the highest priority rule in each group that matches the packet. By default, VFP will find the rule matched by the last group in the list, and that rule can be marked as terminating. Or another way to describe it, meaning that if it ever matches said terminating rule, the match will be applied immediately, and the packet won't have to traverse any other groups. For example, in a stateful firewall, the infrastructure access control list and the customer access control list can be expressed as two different groups in a layer. The blocking rules could be marked as terminating as it is by default. So that way, if either group blocks a packet, that packet will automatically be dropped. So the packet only goes through if both sets of rules in the group allow it to do so. Alright, now rules by themselves are usually not optimal for large mapping tables. For example, doing a customer address to a physical address lookup that VNet requires. VNet uses this to look up outbound traffic with a directory system. So in this case, rules would not be optimal for such a large mapping table. Because of this, VFP supports a resource, which is a port-wide structure that allows any rule on a port to reference it. This structure is a generic structure, which supports, in this case, a hash table of mappings. VFP, resources also allow VFP to handle exception events in the context of these resources. As VFP became increasingly popular, the devs realized that the workloads for which VFP was designed for did not scale very well. VFP version 1 simply used a linear match for rule classifications. Each layer had to reparse a packet as it moved through that relevant layer. In VFP version 2, the developers created a method that would only allow packets to be touched at the end of the pipeline once all relevant match action decisions were made. VFP, the devs did this by introducing a central packet processor, which was created to parse relevant metadata from the packets instead of acting on the packets themselves. The CPP would parse the L2, the L3, and the L4 headers, as you can see in the chart below, for matches, and it would form a flow ID with the values for each of these headers. A tuple of these flow IDs would be pushed together to form a UF ID, or a United Flow ID. The parsing of these header values is usually done by header transpositions, which are the action primitives that can change or shift fields throughout a packet. They're able to provide a list of header actions for many different types of headers. Examples of which you can see on the right for pushing, popping, ignoring, modifying, etc., etc. The key functionality of these HTs is that they allow rule processing handlers to take as input a flow ID and to output some transposition. This transposition could potentially be some other valid VFP flow ID. This implementation allows rules to be designed or implemented without directly touching any packets. These unified flow IDs can then be cached by the flow compiler into a huge table known as the Unified Flow Table, or the UFT. The data path that any packets will take can then be split into a fast path and a slow path. The first packet of some random input TCP flow would take the slow path and run the header transposition engine that we discussed earlier at every layer that it passes through, and perform any potential match actions. Any subsequent packets from this TCP flow could then take the fast path and use this UFT created by the first packet to apply any transpositions directly without having to involve the layers or the rules of the VFP itself. I've provided a example of a diagram for it, as you can see at the bottom of the slide. This caching with the unified flow table is an important component in offloading flows that I will discuss a little bit later on. The flow compiler also has an additional requirement of being transparent to any clients using the VFP API in order to perform their jobs. Any changes to the rules in a layer should be applied to any subsequent packets, even if a unified flow already exists. This is done with the flow reconciliation engine, which solves this issue by using a lazy reconciliation. This is done by any unified flow is reconciled when that unified flow is matched and has a generation number less than the port's current generation number. Anytime a rule in the port policy is updated, the port will have its generation number incremented. Unlike with flow pairing, we can't just reverse the flow ID, usually because unified flow pairs can be asymmetric. For example, say we have a connection that is tunneled to the virtual machine on some inbound path, but on the outbound path it is returned directly without tunneling on the outbound side. Instead, VFP needs to be able to pair connections on the virtual machine side of things instead of on the network side of things. VFP accomplishes this for inbound unified flows, or UFs, by creating an outbound UF by initially reversing the UFID of the packet. After the inbound action, it reverses the UFID of the packet, and then it simulates it through the outbound path of that port. For a new outbound UF, we wait for an inbound packet to create a new inbound UF. When that inbound UF is ready to look up its reverse UFID, we will already have an existing flow ready to pair it with. Once this occurs, we can then use a simple TCP state machine to track this pair of unified flows as a connection. VFP currently uses a bridge in order to forward packets by their destination MAC address to the port attached to the virtual network interface controller created with that MAC address. Another feature is that VFP implements hairpinning. Hairpinning, I gave a quick diagram for it at the bottom of the page there, but hairpinning basically enables high-speed gateways without overhead of sending packets to a virtual machine. Another important feature that it offers is that it provides max cap policies on any transmit or receiving of packets to ports on a switch. And this is obviously a quality of service ability that VFP's switching model provides. Some other operational considerations made for VFP include rebootless updates. This allows, the developers accomplish this by first pausing the current data path, detaching the old VFP from the stack, uninstalling it, then installing the new VFP, attaching it back to the stack, and then restarting the data path. This entire process, while it might seem like it would take a long time, usually happens in less than a second. Another operational consideration made for VFP was that it provides a set of functions that can version every VFP object, including layers, rules, flows, etc., with a serialization and deserialization handler. These set of functions are referred to as state, save, restore, or SSR. VFP also provides a very robust set of debugging diagnostics, and I provided a couple of examples of the diagnostics that are possible that VFP can produce at the bottom of the slide. The devs also provided multiple types of hardware offloads. They supported stateless tunneling offloads, where they would program things like stateless checksum, segmentation, receiving scale offloads. They would program these things directly into the network interface controllers that they use. They also provided quality of service offloads, where they selected commercial network interface controllers that support things like transmit max caps, bandwidth reservations, and various other things, all of which are offloaded through a specific interface. This helps to remove some of the overhead of applying it through software alone. In order to ensure that no packets traverse the host, the VFP devs supported the offloading of unified flows instead of offloading software-defined network policy. The offloading of these flows is done via a large hash table via inexpensive dynamic random access memory.
After Jason introduced the implementation, I want to show everybody the evaluation of performance. If you look at figure 9, there are 4 diagrams, shows some information. The packet classifier improves over linear match by 1 to 2 orders. UFT caching improves performance as more layers are added due to VFP fast paths. VFP version 2 scales very well versus VFP version 1. In the last diagram, it shows packet direct improves received packet per second by over 60%. Also, I want to show some results VFP has impacted on. Since 2012, there are 21 major releases of VFP that all run on Azure servers. They have reached petabits per second of traffic. They provide load balancing for exabytes of storage of hundreds of data centers in over 30 regions. As we have learned from this class, load balancing is very critical for a distributed system. VFP public release as a part of Windows Server 2016 become a very important milestone. All goals of VFP have been achieved. Multiple independent controllers can successfully program VFP. VFP treated every connection stably. There's no change to VFP required when changes in other policy occur. There are dozens of rebootless updates to VFP taking place. UFP improved VFP performance dramatically. VFP packet classification speed up classification on real production workloads. Also, VFP flows successfully offloaded to programmable hardware. Now it comes to conclusion. I will show some conclusion about this research paper. Daniel Firestone presented an organized paper by first stating requirements of a virtual switch. Then he shows why current outside implementation were insufficient. And then he introduced the VFP, showed how it satisfied requirement of a virtual switch for Microsoft. This paper assumed that its reader had a strong background in networking, just like everybody in this cloud computing class. It required us to do some Googling of technical terms and networking practices. Some lesson that Jason and I have learned from this paper. Besides some fundamental concepts, we have learned how to design for stiffness from day one. We know layering is very critical, and the go-to-table module is harmful. We learned LAAS cannot handle downtime. So Jason and I have discussed a little bit about the difference between LAAS and PAAS. Now we know how to design for serviceability, how to decouple the wire protocol from the data plan. Now we know how to design for E2E monitoring. These are some critical lessons we have learned from this paper.
All right, some of our final thoughts on the paper. VFP isn't necessarily a novel concept, as there are already vSwitches out there in the wild, such as OpenVS and Google's own implementation of the vSwitch. However, I think VFP makes its salt by proving that it can offer a vSwitch that is ultimately scalable in a large cloud environment, such as the one hosted by Azure. The overall importance of vSwitch isn't about the details of the features that it provides, but the fact that it happened at all. Providing innovation in the vSwitch part of the software-defined network technology space will hopefully lead future devs towards more innovation on the back of the success of VFP. At the end of the day, VFP accomplished all of its stated requirements and provided a great solution for what Microsoft desired. My personal favorite being the rebootless updates, which proved once again that no matter the piece of tech or component or software, that end users today expect little to no downtime when they are utilizing your services. All right, that brings us to the end of our presentation. Me and Maggie would like to thank you guys for watching through this entire video. We hope it was insightful. And for the rest of the CS 643 students watching this, best of luck to you guys in the rest of the semester.